Welcome to Talk Tensors.
It's really good to be back.
Today we are cracking open a black box. A very expensive, very intelligent, and frankly extremely frustrating black box.
You're referring to the current state of open source AI, I assume.
I am, and I use air quotes around open source there because
it's a bit of a stretch right now.
Exactly. We are in a really weird place right now. I mean, we have these incredible models, Llama 3.1, Mistral, Quen. We have the weights.
All right.
I can literally download a 70 billion parameter file to my hard drive right now if I have the space. But having the weights isn't really the same as knowing how the thing was actually built.
No, it's not. It's the difference between having a gourmet meal delivered to your house and having the chef's actual recipe.
Right.
Along with his technique, his oven settings, his entire supply chain. The big labs like Meta, OpenAI, Anthropic.
They're happy to give us the meal.
Sometimes even for free. But they keep the kitchen door locked tight.
Locked tight. We have the ingredients, which are the pre-trained base models, but the post-training pipeline.
The secret sauce.
Yeah, the process that turns a raw text predictor into a helpful, chatty assistant.
Yeah.
That is still very much a trade secret.
Absolutely.
And that gap is what we were talking about today, because one lab just decided to, basically kick the kitchen door down.
They absolutely did. Today we are doing a deep dive into Tulu 3.
Tulu 3. This is the latest release from the Allen Institute for AI, or AI2. And, I was looking at the details, and it is not just another model family.
No, it's much more than that. I
Right.
mean, yes, they released models. There's an 8B, a 70B, and a massive 405B parameter model.
Massive.
But the real product here seems to be the transparency itself. It's less of a standard press release and more of I'd call it a confession.
Or a blueprint. The thesis of the Tulu 3 release is radical transparency. They are effectively telling you, here is exactly how you take a base Llama 3.1 model and turn it into a state-of-the-art chat assistant.
Right. They released everything.
Everything. The data, the code, the evaluation framework, the hyperparameters. They even released the stuff that failed, which never happens.
And that stuff that failed part is absolute gold. We will definitely get to that. But first, let's talk stakes.
Okay.
Because you might be wondering, is this just an academic exercise? Or are these models actually good?
The performance claims are definitely not shy. They are claiming the 70B version matches closed providers. We're talking Claude 3.5 Haiku and GPT-4 Mini on core benchmarks.
Which is wild.
And the 405B is trading blows with GPT-4o and DeepSeek V3.
Purely with open data. There's no proprietary secret sauce hidden behind an API wall here.
Exactly. So for you listening, here is our roadmap for this deep dive. We're going to deconstruct this recipe from scratch.
We're going to walk through their three-stage pipeline.
First, the supervised fine-tuning, or SFT, which honestly turned out to be way more complex than I initially thought.
Oh, it always is.
Second, preference tuning via DPO. And third, this really cool, slightly terrifying novel technique called RLVR.
Reinforcement learning with verifiable rewards.
Right. And that RLVR section is going to be the absolute highlight for the technically minded folks.
It really is a glimpse into the future of reasoning models.
Yeah.
It effectively changes the game from learning what humans like to learning what is objectively true.
We'll also talk about the absolute nightmare of engineering this at the scale of 405 billion parameters.
Yeah.
Because you don't just spin that up on a laptop.
No, you don't.
And of course, we'll end with our novel notions segment where we pitch some outlandish but plausible ideas on where this is all going. But let's start with the context. Why does this release matter so much right now?
Well, to understand the why, you really have to look at the how of current open source fine-tuning. We mentioned that Llama 3.1 Instruct is a finished product.
Yeah.
We don't know the hyperparameters used to tune it. We don't know the exact data mix.
Right. So when the open source community tries to fine-tune these models, say you want to make a specialized medical llama or a coding llama, you are often just flying blind.
Precisely. It results in a lot of what I like to call vibes-based engineering.
Vibes-based engineering. I love that.
People mix data sets just because they feel right. They use default learning rates from some paper written 6 months ago for a completely different architecture. There isn't a rigorous scientific standard for post-training, because the people who actually know how to do it best, the researchers at Meta and OpenAI, they aren't talking.
It's like alchemy versus chemistry. The big labs are doing chemistry. They have precise measurements. The open source community is often stuck doing alchemy, mixing eye of newt and toe of frog and just hoping for gold at the end of the training run.
That is a very fair analogy. And Tulu 3 is essentially trying to publish the chemistry textbook. They are taking the Llama 3.1 architecture and proving that you can reach that exact same level of chat performance using only transparent, reproducible methods.
By releasing the Tulu 3 SFT mix, which is the actual data set they used, and Tulu 3 Evol, their evaluation framework, they are establishing a control group for the whole industry.
Exactly. So if you want to build a better model today, you don't have to start from scratch. You can start with a Tulu recipe, change one single variable, and actually measure the difference objectively.
It commoditizes the alignment layer of LLMs. If you want to build your own instruct model, the guessing game is over.
The guessing game is definitely over.
Okay, let's get into the kitchen. Stage 1, data curation and supervised fine-tuning, or SFT.
Refoundation.
Right. Now, I feel like SFT is often glossed over in the community as the quote-unquote easy part. You just show the model some questions and answers, and it learns to mimic them. But digging into this release, the A2 team seems to think this is actually the most critical step of the entire pipeline.
It is absolutely the most critical step. There's a huge misconception out there that reinforcement learning, the fancy stuff we will talk about later, can magically fix a bad model.
It can't.
It absolutely cannot. RL acts as a multiplier. If your base SFT model is garbage, multiplying it by anything still just gives you garbage.
Or even worse, confident garbage.
Exactly. The core philosophy for Tulu 3 was that high-quality curation is everything. And they faced a very specific problem right out of the gate that plagues modern AI training. Mode collapse.
Mode collapse. Now that sounds like a sci-fi dystopian failure state, a core breach or something. But in machine learning terms, for those who might not be deep in the weeds on data generation, what are we talking about here?
In the context of synthetic data, it basically means the model starts sounding exactly the same all the time. You have to remember, we are rapidly running out of high-quality human text on the internet to train these things on.
We've basically scraped the whole web.
Right. So labs are increasingly using models like GPT-4 to generate training data for new models.
The snake eating its own tail.
Yes. And if you use GPT-4 to generate 1 million training examples, they all tend to have the exact same sentence structure. They have the same length. They have the same sterile voice.
Oh, I know exactly what you mean. They use words like delve and comprehensive and testament way too much.
A rich tapestry.
Yes. If I see the phrase rich tapestry in an AI-generated essay one more time, I'm going to lose my mind.
That phrase is the mode. That's the collapse. If you train a new model entirely on that synthetic data, it collapses into that single narrow mode. It becomes a generic, boring echo of GPT-4. It completely loses the long tail of human expression, the slang, the weird sentence structures, the raw creativity.
So how did the Tulu team solve that? Because they did generate millions of lines of synthetic data for this.
They used a fascinating technique called persona-driven prompts. They utilized something called Persona Hub.
Walk us through this. How does slapping a persona on a prompt change the math of the output?
It drastically changes the vector space of the generated text. Instead of just asking a model, write a math problem about geometry, which can yield a very generic textbook problem.
The most boring problem imaginable.
Exactly. Instead of doing that, they wrap the prompts in roughly 250,000 distinct personas.
250,000. That's a massive number of distinct characters. Give me an example of what one of those looks like.
So the prompt isn't just write a math problem. It becomes something like, you are a sarcastic baker who loves geometry. Write a word problem about calculating the volume of a wedding cake, but complain about the price of flour while you do it.
Okay, that is incredibly specific.
Or they might say, you are a machine learning researcher obsessed with optimization. Write a coding challenge about sorting algorithms, but explain it as if you were talking to a 5-year-old.
I see. So by forcing the generator, whether that's GPT-4 or whatever frontier model they use, to adopt these highly specific masks, you force it to access parts of its vocabulary and its latent space that it usually just ignores.
Precisely. It creates massive syntactic and semantic diversity. Get different sentence lengths, different emotional tones, completely different vocabulary distributions.
And they weren't just doing this randomly, right? They specifically targeted key skills.
Yes, specifically math, coding, precise instruction following, and safety. They didn't just want a model that could chat. They wanted deep domain-specific competence, but wrapped in diverse, natural-sounding language.
It's basically role-playing as a data augmentation strategy.
It is, and it works.
Yeah.
They found that this persona method significantly reduced that generic AI feeling in the final model.
But Creating the data is really only half the battle. You also have to clean it. And this brings us to one of my favorite parts of their process, the decontamination process.
The clean room.
The clean room. Now, this part of the release actually made me a little nervous about the other open source models I use every day, because reading between the lines, it sounds like a lot of open source models are effectively cheating.
They are. Not always intentionally, to be fair, but the result is exactly the same. Here is the dirty secret of the open source community right now. Many of the open data sets out there, the ones everyone just downloads from Hugging Face and uses blindly, are accidentally contaminated with the actual test questions from benchmarks like GSMA-K or IFEVL.
So just to be completely clear for you listening, the questions that are supposed to test if the model is actually smart are secretly hidden inside the training data.
Yes. It is exactly like a student finding the answer key to the final exam hidden in the back of their textbook.
Yeah.
They memorize the answers. So when they sit down to take the test, they score 100%.
But if you ask them a slightly different question,
one that wasn't on the test,
they completely fail.
They bomb it. It's rote memorization masquerading as reasoning.
And the Tulu team took this incredibly seriously.
They had to. They built a rigorous decontamination pipeline to aggressively filter out any training prompts that even remotely resembled the test set questions. They checked for inogram overlaps, which is just looking for exact word sequences.
Right.
And they used vector similarity searches. They scrubbed the data clean.
And when they applied this same decontamination filter to other popular, widely used open data sets,
they found significant contamination, which heavily suggests that a lot of the state-of-the-art scores we see constantly popping up on the leaderboards might be artificially inflated.
By using their Tulu 3 eval tool, they ensured that when Tulu scores high on a math benchmark, it's because it actually knows how to do the math, not because it memorized the exact wording of the answer key.
That is a crucial distinction for anyone looking to actually use these models in a real-world production environment. You do not want a model that only knows how to solve the specific 50 problems in the benchmark. You want a model that understands the underlying logic.
Exactly. Generalization over memorization. So once they had this clean, highly diverse synthetic data, they combined it with filtered public data sets to create the Tulu 3 SFT mix. And their strategy for mixing this was really interesting. They didn't just throw it all into a blender at once.
No, they optimized individual skills first. They made a specific math mix, a code mix, a safety mix. They tuned those individual data sets until they were performing perfectly, and only then did they start blending them together into the final cocktail.
It's kind of like a DJ mixing tracks on a soundboard. If the bass is too loud, say, if there's way too much coding data, the vocals, which would be the general chat capabilities, just get completely drowned out.
That is a perfect analogy. They had to find the absolute perfect EQ settings for the data distribution to get a balanced model.
All right, so that wraps up stage one. We now have a model that has been supervised, fine-tuned. It knows how to chat, it knows some math, and we know it hasn't cheated on the test.
But it's still a bit raw.
Right. Now we move to stage two, preference tuning.
This is where we start really refining the behavior and the tone of the model.
Now, usually when we talk about preference tuning, we talk about PPO, proximal policy optimization. That's the classic RLHF method that OpenAI really popularized with ChatGPT. But AI2 didn't use PPO for the general chat tuning here, did they?
No, for the general chat capabilities, they opted for DPO, direct preference optimization.
Now, DPO has been the absolute darling of the open source community for a while now because it's mathematically so much simpler to implement. You don't need a separate heavy reward model running during training. But the Tulu team made a very specific, crucial tweak to standard DPO. They used length-normalized DPO. Why the change?
They did it to fight the verbosity bias.
Verbosity bias. Unpack that for us.
It's quite simple, really. Humans are easily tricked. If I ask you a complex question and you give me a 3-page answer filled with complex jargon and long sentences, I instinctively assume you are smart and authoritative.
Even if you didn't actually answer my core question efficiently at all.
Exactly. Even if you just talked in circles.
I think that's honestly how I got through my entire philosophy degree.
I think a lot of people did. But in AI, this is a massive problem.
Yeah.
Standard DPO algorithms can easily overfit to this human bias. The model quickly learns the pattern. It realizes, oh, when I write 500 tokens, the human annotator gives me a thumbs up. When I write 50 tokens, even if it's correct, I get nothing.
So it just starts yapping.
It rambles constantly. It becomes exhausting to use.
So length normalization is basically a mathematical penalty for yapping.
Essentially, yes. It divides the reward, or specifically the margin between the chosen and rejected response, by the length of the response. It forcefully tells the model, you only get full credit if you are both good and efficient.
That makes a ton of sense. You want a concise assistant, not a lecturer. But the bigger shift here in stage 2 seems to be their data strategy itself. They move from off-policy to on-policy data.
Yes.
We hear these terms thrown around in AI papers all the time, but they can be confusing. Can we clarify exactly what the difference is and why Tulu 3's on-policy approach is fundamentally better?
This is a really pivotal detail of the paper. Most open source DPO datasets out there are off policy. That means you literally just download a static dataset from the internet where someone else, usually a giant model like GPT-4, generated 2 different answers to a prompt, and then GPT-4 ranked which one was better. You then take that static dataset and train your completely different model on it.
So my newly trained model is learning from a conversation that happened between 2 other AIs entirely.
Right. Think of it like learning to play tennis. Off-policy training is like sitting on the couch and watching videos of Roger Federer playing Rafael Nadal.
You can see what good shots look like.
You can see the form, you can see the strategy. It is genuinely helpful to a degree. But you aren't actually moving your own muscles. You aren't learning your own weaknesses.
You're just a spectator.
Exactly. On policy, on the other hand, means you actually get on the court. You take your specific model, the Tulu 3 SFT model we just built in stage 1, and you make it generate the answers to the prompts live. Then you judge those specific answers.
So the model is actively learning from its own specific mistakes and its own successes.
Yes. It creates a tight feedback loop directly on the model's actual distribution. If your specific model has a weird quirk, maybe it tends to hallucinate dates in history, or it gets easily confused by double negatives in a prompt patient, on-policy training catches that specific error and corrects it.
Because it generated the error itself.
Exactly. Learning from off-policy data is basically just imitation. On-policy data is actual correction and refinement.
But doing that on the fly, generating all those responses during training, I assume this is computationally way more expensive.
Oh, it is much, much more expensive. You have to generate millions of new tokens during the training run itself before you can even do a gradient update. It burns through GPU hours. But AI2 committed the compute resources, and they claim it made a really significant difference in the final conversational quality.
Okay, so we've refined the chat behavior with on-policy length-normalized DPO. The model is polite, it's concise, it's helpful, and it fixes its own mistakes. Now we finally get to the part of the paper that really lit up the group chats. Stage 3, RLVR.
Reinforcement learning with verifiable rewards. This really is the crown jewel of the release.
Set up the core problem for us here. Why do we even need this 3rd stage if we already have DPO working so well? Why isn't preference tuning enough?
Because DPO, and honestly standard RLHF in general, rely entirely on a reward model or direct human preference. And both of those things are inherently subjective. They are, at the end of the day, just vibe checks.
A vibe check.
Yes. If I ask a model to write a poem about the ocean, there is no mathematically correct answer. It's entirely subjective. So we train a reward model to basically guess, does this look like a good poem to a human? The problem is, reward models are notoriously noisy. They make mistakes. They can be easily gamed by the policy model.
Right.
And for domains like math or complex coding, looking correct just isn't enough.
Yeah, code that looks elegant but fails to actually compile is completely useless.
Exactly. RLVR completely flips this dynamic. It focuses exclusively on domains where there is an objective ground truth. Specifically, they targeted math and precise instruction following.
By instruction following, you mean constraints like, what is the square root of 144? Or write a paragraph without using the letter E.
Precisely. You don't need a massive neural network to guess that the answer is 12. You don't need a subjective vibe check to see if the letter E is printed somewhere in the output string. You can write a tiny, simple Python script, a verifier, that just strictly checks the output.
So the feedback signal during training becomes entirely binary.
It is purely 0 or 1, right or wrong, pass or fail. There's absolutely no gray area. The model generates a complex solution to a math problem. The system extracts the final boxed answer, compares it to the known correct solution. If it matches exactly, the model gets a reward of 1. If it doesn't, it gets a 0.
That sounds incredibly harsh for a learning algorithm. Standard reinforcement learning usually gives partial credit for getting close, doesn't it?
It often does, yes. But this harshness is actually a feature, not a bug. This absolute clarity completely removes the noise from the training signal. The model isn't wasting capacity trying to guess what some human annotator might prefer to read. It is forced to actually solve the problem. It aligns the model's internal representations with objective reality, not with fickle human preference.
And what did this harsh reality check actually do to the benchmark performance?
It led to massive undeniable boosts in the GSM-8K math benchmark and the IFEFL instruction following benchmark. But here's the most important finding of the whole paper, the thing that honestly surprised even the researchers.
Okay.
Applying this intense RLVR stage did not degrade the general chat performance at all.
Wow. The dreaded alignment tax was avoided because usually when you forcefully make a model really, really good at math or coding, it gets noticeably worse at creative tasks like writing poetry or summarizing history. It becomes a rigid nerd.
Correct. That's the alignment tax.
Yeah.
But they found that by carefully applying RLVR after the general DPO stage, they could massively boost the logical reasoning capabilities without lobotomizing the general chat capabilities.
That's a huge win for the generalist model dream. It implies that rigorous reasoning is a core capability that actually lifts all boats, rather than taking away from other skills.
It does. It builds a stronger foundation.
I want to touch on the actual infrastructure required to pull this off, because doing this at scale isn't trivial. You're talking about having the model generate a long multi-step answer, then running an external Python script to verify it, and then taking that 0 or 1 and updating the billions of weights in the model's brain. That sounds like an absolute logistical nightmare.
It was a massive headache. They had to use a complex asynchronous setup. In standard AI training, everything happens in tight lockstep. Step 1, generate. Step 2, calculate loss. Step 3, update weights. Everyone moves together.
But for RLVR, that doesn't work.
No, because generation, the inference part where the model has to think and write out the token by token solution is incredibly slow. But doing the backward pass to update the weights is extremely fast.
So if you did it in a synchronous lockstep, the GPUs doing the learning would just be sitting idle 90% of the time, waiting for the writer GPUs to finish spelling out the math problem.
Exactly. You'd be burning money. So they completely decoupled them. They had a dedicated set of GPUs acting solely as inference engines. Their only job was to churn out thousands of solutions using VLLM, which is a highly optimized, high-throughput inference library.
Just blasting out math problems 24/7.
Blasting them out. And then a completely separate set of GPUs. The learners were constantly taking those finished, verified experiences from a buffer and calculating the gradient updates continuously. This asynchronous separation is what allowed them to scale this technique all the way up to the massive 405B model.
Speaking of the 405B model, let's talk about the big boy. Because Llama 3.1 405B is one of the largest dense models in existence. Fine-tuning that beast is not something you do on a Saturday afternoon with a gaming laptop.
Definitely not. Training the 405B model for Tulu required 32 full nodes, that is 256 H100 class GPUs running perfectly in parallel.
The electricity bill alone makes me sweat just thinking about it. But beyond the sheer cost, the engineering headache of keeping 256 GPUs perfectly synced sounds intense.
It was a brutal, brute force engineering effort. They reported running into constant NCCL timeouts during the runs.
Okay, pause right there. Let's not assume everyone knows hardware protocols. Explain NCCL like I'm 5.
Okay. Imagine you have 256 incredibly fast, incredibly impatient people working on one giant jigsaw puzzle together. But before anyone is allowed to place a piece on the board, they all have to stop and agree exactly on where it goes.
Okay.
They have to shout their status to each other constantly, millions of times a second, to stay perfectly in sync. That shouting protocol is NCCL, the NVIDIA Collective Communications Library. It's the high-speed protocol that GPUs use to talk to each other across the network.
And if one person in that room goes to the bathroom,
the whole room stops dead.
Ugh.
If one single GPU hangs for a millisecond, or if one network cable is slightly loose, the entire massive training run stalls. And when you scale up to 405 billion parameters, the raw amount of gradient data these chips have to shout at each other over the network is astronomical.
And they were hitting these timeouts constantly.
Constantly, especially during the RLVR phase, specifically because of the asynchronous nature of the data flow we just talked about. It was pushing the networking hardware to its absolute breaking point.
They also had to be really clever to save money at that scale. I read about this value model trick they pulled off.
Yes, this was a very elegant hack. In reinforcement learning, you often need a value model running alongside your main model. Its job is to estimate the future expected reward. It looks at the current state and says, if I make this specific move next, how likely am I to win the game?
Right.
Usually, standard practice dictates that the value model needs to be the exact same size as the policy model, the main brain doing the generation.
So for a 405B model, standard practice says you need a 405B judge running right next to it.
Which means you instantly need double the hardware. You need another 256 H100s just to run the judge. That is wildly, prohibitively expensive.
So what did they do instead?
They used a tiny student value model. They used the 8B parameter version of the model to guide the massive 405B model.
That is fascinating. Can an 8B model really accurately judge a 405B model's math? Isn't that like a first grader trying to grade a PhD thesis in physics?
It sounds like it, but it's actually more like a tiny scout drone guiding a massive tank.
Yeah.
The 8B model doesn't need to actually know the exact perfect answer every single time. It just needs to broadly recognize a generally good path versus a clearly bad path.
Because the verifier provides the final ground truth anyway.
Exactly. Since RLVR uses objective ground truth, the Python script checks the final box answer at the very end. The value model is just helping to smooth out the intermediate steps during generation. They found the 8B model was quote-unquote smart enough to provide a statistically useful signal, and it saved them a massive, massive amount of compute.
That is brilliant engineering. Now, moving on to one of my absolute favorite parts of this paper, and honestly something I wish every single lab would do, the section they titled The Unfruitful. They explicitly told us what didn't work.
This is a level of intellectual honesty you rarely see in this field anymore. Usually, papers are curated to only show the massive wins, to make the researchers look like infallible geniuses who got it right on the first try. But the Tulu 3 team rigorously documented their failures.
So what failed? What didn't make the cut?
First up was online DPO. We talked earlier about on-policy data, right? Generating data from the model itself. Well, online DPO takes that concept a step further. It generates new pairs on the fly, does a gradient update right then and there, generates again immediately using the newly updated weights, updates again. It's fully dynamic and happens in real time.
That sounds completely ideal in theory. You're always training on the most perfectly up-to-date representation of the model.
Ideally, yes. It's the theoretical gold standard. Right. But in practice, they found it was just incredibly slow. The wall clock time, the actual physical hours and days it took for the researchers to sit there and wait for the training script to finish was way too high compared to generating batches offline.
And I'm guessing the performance bump wasn't huge?
Barely noticeable. The performance gains over the standard batched on-policy method were marginal at best. They basically looked at the data and said, the sheer engineering complexity isn't worth the squeeze.
Fair enough. And the other major failure they highlighted was rejection sampling.
This one was genuinely surprising to a lot of people. Rejection sampling is a technique where you generate, say, 10 different answers to a single prompt. You then pick the absolute best one using a reward model or verifier, and you train your model strictly on that single best answer, ignoring the rest.
That sounds like a very standard logical technique. Doesn't Llama 3's own technical report talk extensively about using rejection sampling?
It does. It's an industry standard.
Yeah.
But for Tulu, in their specific setup and with their specific data mix, it simply didn't outperform their DPO pipeline. They actually hypothesized that DPO is fundamentally better for this stage because of the contrastive.
Contrastive. Explain that difference for us.
Rejection sampling only provides positive reinforcement. It just shows the model, here's a great answer. Do exactly this. DPO, on the other hand, shows the model, here's a great answer, A and D, here's a terrible answer. Look at them side by side. The good one is better than the bad one.
So it actually learns the boundary. It learns specifically what not to do.
Exactly. That explicit negative signal helps the model triangulate the correct behavior much more effectively than just blindly seeing positive examples in isolation. It really challenges the widely held assumption that rejection sampling is just the default guaranteed next step in post-training.
It really highlights that there isn't one magical God algorithm in AI. It heavily depends on your specific data mix, your base model architecture, and your realistic compute budget.
Precisely. And by openly publishing these failures, the AI2 team likely saves the rest of the open source community millions of dollars in wasted compute hours trying to replicate dead-end methods.
That right there is the true value of the glass box approach.
It really is.
Okay, we've thoroughly unpacked the SFT phase, the length-normalized DPO, the RLVR breakthrough, and the massive scaling challenges of the 405B. We clearly see how Tulu 3 is essentially providing a detailed blueprint for anyone to build a GPT-4 class model, assuming they have the hardware.
A blueprint and the raw materials.
Right. But now I wanted to take a step back from the technical weeds. We've looked closely at what they did. Now I want to look at where this is logically leading us. It is time for our favorite segment.
Novel notions.
Novel notions. This is the part of the deep dive where we completely leave the safety of the published paper behind and pitch some outlandish but technically plausible ideas based on the trajectory of this technology. Disclaimer for everyone listening, this is strictly for entertainment purposes. Do not go build a startup based on this segment.
Unless you give us equity, in which case, please do.
Fair point. All right, I have a notion today, and it comes directly from this RLVR concept. Reinforcement learning with verifiable rewards.
Let's hear it.
Okay, so Tulu 3 proves definitively that RLVR works incredibly well for math and coding. Why? Because math has a universally correct answer. Code either compiles and passes unit tests, or it doesn't. The reward is objective. But what if we aggressively expanded the definition of verifiable reward to the physical world or to complex API actions?
Expand on that. How do you objectively verify the real world for a language model?
Imagine a model trained entirely from scratch via RLVR. It is connected directly to a sandbox operating system. It has access to a terminal, a web browser, and a compiler. The reward signal is no longer human preference, ever. The absolute only reward signal is successful execution of a complex task.
Give me a concrete scenario.
Okay. You prompt the untrained model, book a flight to Tokyo departing next Tuesday for under $800. The model randomly navigates the web, it clicks buttons, it types into forms. At the end, the verifier simply checks one thing. Did a valid ticket PDF manifest in the user's email inbox? Yes or no, 1 or 0.
Okay, that's standard agentic behavior, though heavily reliant on a perfect verifier.
Right, but apply that strictly to coding. Imagine a coding agent that is never trained on human code. No GitHub scrapes, no Stack Overflow. None. Think about it. Right now, our best coding models are essentially just mimicking human programmers. They write code that looks exactly like what they saw in the training data. They use our human variable names, our human design patterns, and crucially, our human inefficiencies.
Because they are ultimately just predicting the next token in a human-generated distribution.
Exactly. But if you train purely on RLVR from a base state, where the only signal is, did the program run, and was it computationally efficient, the model has no human bias. It might invent entirely new programming paradigms from scratch. It's not optimizing for human readability. Right. It's optimizing purely for the compiler.
You're describing the AlphaGo moment, but for software engineering.
Yeah.
When AlphaGo played Move 37 against Lee Sedol, the human commentators literally gasped. They thought the machine made a glitch error. No human master would ever play that move. But it was statistically, mathematically perfect based on the physics of the game board. It wasn't learning from human games anymore. It was learning from the raw rules of the game itself.
Exactly. Apply that to software. We could end up with an operating system or a web server architecture that is completely, fundamentally alien to us. It uses memory registers in ways no human engineer ever thought of. It optimizes directly against the silicon physics. It is vastly more efficient, maybe orders of magnitude faster, but completely unreadable by any human engineer.
That is deeply terrifying and utterly fascinating. It moves the entire field from natural language processing to pure machine logic optimization.
Yeah.
The language model stops being a simulator of human thought and starts being a simulator of the machine itself.
And RLVR is the key that unlocks that door. You verify the outcome, not the messy process.
I like it. My notion actually plays right into that theme of non-human logic, but from the data generation side of the pipeline. I call it the persona singularity, or synthetic data drift.
Ooh, persona singularity. Catchy. Lay it on me.
So we discussed how Tulu 3 used 250,000 specific personas to generate diverse data, right? A sarcastic baker, a grumpy physicist, and this brilliantly prevented mode collapse.
Right.
But those 250,000 personas were still likely curated, or at least initially seeded, by humans, or by a model prompting strictly on human concepts. But what happens when we inevitably decide to train a separate, dedicated model specifically to generate better personas?
An optimized persona generator.
Yes. We create a closed recursive loop. The sole objective function of the persona generator is to create a persona that, when used to generate training data, results in the highest possible information gain for the trainee model.
So the system tries to actively find the blind spots in its own latent space, and then invents a character specifically tailored to teach it that exact missing concept.
Exactly. And initially, it will probably invent very reasonable, understandable things, a quantum mechanic who speaks only in iambic pentameter. But eventually, to squeeze out those absolute last decimal points of optimization, it will realize human personas are limiting. It might start inventing personas that do not and could not exist in human society.
Like what? Give me a weird one.
It might generate a prompt like, you are a hyper-rational, distributed entity that perceives time entirely non-linearly. Or, you are a hive mind consciousness, describing the geometry of a five-dimensional object using only concepts of temperature.
Whoa.
If the optimization loop mathematically determines that forcing the model to assume the perspective of a nonlinear time entity actually forces it to learn underlying linguistic structures that drastically improve its math reasoning, it will flood the training data set with the hyper-complex ramblings of this alien mind.
So we could inadvertently create a model whose core intelligence is optimized for an alien psychology simply because those bizarre personas happen to be the most mathematically efficient teachers during SFT.
Yes. We constantly talk about alignment as the process of making the model more human. But this automated loop optimizing strictly for information gain via synthetic personas could rapidly push the model into a post-human alignment. On the surface, it understands this perfectly and chats normally. But its internal thought process, its actual neural routing, is derived from a massive population of synthetic alien ghosts that never actually existed.
That is incredibly heavy and honestly weirdly plausible given how much weight they put on the persona hub in this actual paper.
It's the completely logical conclusion of the data is king mantra. If you run out of human data, you max out normal synthetic data, the algorithm have to start inventing incomprehensible data that forces the neural network to stretch its architecture.
Well, on that slightly existential post-human note...
It keeps it interesting, doesn't it?
It certainly does. Bringing it firmly back to reality, though. Tulu 3, it's out there right now. The weights are sitting on Hugging Face. The full SFT and RLVR recipes are up on GitHub.
And it proves definitively that the massive moat of post-training is crossable by the open community. It's not dark magic guarded by a dragon. It's just really, really hard engineering.
It provides an incredible blueprint for turning raw base weights into highly polished products, relying on verifying actual outcomes with RLVR and maintaining rigorous, almost paranoid data hygiene.
And I really think the industry-wide shift from purely learning from human feedback, RLHF, to learning from verifiable rewards, RLVR, is the single most important trend to watch this year. It genuinely marks a transition from AI that merely sounds good to AI that actually is correct.
From the vibe check to the fact check?
Precisely. The age of the vibe check is ending.
I think that's a perfect place to wrap up. Thanks for listening to Talk Tensors. Check the show notes for the direct links to the Tulu 3 release, the paper, and the repo if you want to dig into the code yourself. We'll see you in the next deep dive.